Hello everyone, I'm Xiaofeng Gao from UCLA. Today I'm going to talk about our paper Joint Mind Modeling for Explanation Generation in Complex Human-Robot Collaborative Task. So our human collaborators can work towards the success of a common goal. In such a team, one member may only be responsible for a certain small part of the whole task. In that case, communication is often necessary to coordinate each other's work, especially their overlaps or depended upon each other. To make the communication more efficient, we often infer others' mind, essentially what they know about the situation and what specific goals they are trying to accomplish, and compare them to the knowledge we have. Such mind-aware communication minimizes discrepancy among collaborators' minds and is crucial to the success in human teaming. We believe robots that collaborate with humans should go through the same communication process. Let's take this collaborative cooking game for example. In this game, the human and robots need to make apple juice with 3 apples. The task requires the agents to be responsible for different subtasks. Specifically, the robot is in charge of collecting the apple and using the juicer, while the human needs to use the chopping board and deliver the juice. As you can see, some subtasks have dependencies. Their preconditions would be met only upon the completion of the other subtask. For example, the robot cannot use the juicer if the apple is not cut by the human and placed on the table. We are interested in the problem that how can the robot communicate with its non-expert human partners and coordinate their actions to finish such a complex task. To solve this problem, we first enable the robot to generate a joint task plan, which is essentially what it plans to do itself and what it expects user to do at each time step. Technically, we take this mixed integer linear programming approach, which the robot is optimizing the amount of time for the slowest agent to finish the task by allocating subtasks to both agents. Motivated by human and human communication, we want to enable our robot to generate explanations, telling the user what to do and what the task is all about when the user gets stuck. So we propose the explanation generation framework based on inferring human intentions. If the robot believes the task plan the user has in his or her mind is not optimal compared to the robot's own plan, the robot will generate explanations. To deal with the situation that users have already finished some things that cannot be undone, we allow our robot to do this replanning to generate new task plans. Our human mental model is built upon the Bayesian inference of user actions, which basically integrates the prior knowledge and likelihood from the new data. We assume user communication and their observed actions are independent, and we compare partially observed user trajectory to the sample trajectory to understand what actions the user is trying to perform. In this demo, the robot is trying to infer the subtask the user is trying to perform based on the distance between the observed user action sequence and the sampled user action sequence. And a reasonable prediction for the user's action would be taking the bowl. For explanation generation, we're essentially answering this what to say and when to say problem. For explanation content, we're communicating the expected subtask and atomic actions of both agents. We also show that what's the possible state change caused by a certain atomic action. For explanation timing, we allow the robot to communicate this explanation when the expected user subtasks are different from the inferred subtask. In this example, the human is after the human cuts the apple, it gets confused about what to do next, and the robot is trying to generate explanations, telling it to place the apple on the table. we recruited 27 non-expert users from the university subject pool, and each user is randomly allocated into one group. The user would first go through an introduction phase, where they get an explanation template. After that, the user would go through the familiarization stage, where we ask users to finish a simple task to help them get familiar with the control of the game. After that, in the testing stage, the user would get different explanations based on their assigned group. Users in the control group would not receive any explanations, and users in the heuristic group would get explanation when there is no detected user actions for a while. This is served as a behavior indicator that users didn't know how to proceed. In the mind modeling group, the users would get explanations based on our proposed algorithm. Finally, the users would evaluate the performance of the robots in the post-experiment survey. In our experiments, our participants played 2 rounds with the machine for the same task, which is making apple juice. During the task, we measured the task completion time in both rounds. The line plot shows that our explanation generation framework helped the user to finish the task more efficiently on their first run, while those in the control group need to complete a task one more time to be able to finish it with the same efficiency. We also observed that users in the mind modeling group viewed the robot as a more helpful and efficient team member, which confirmed our hypothesis. For future work, we like to make the tasking environments more complicated so that the robot and human can have a shared workspace and more diverse collaboration strategies can emerge. In the current work, we assume human doesn't know much about the task, and we let robot play a leading role in the team. In the future, we like to focus on more balanced settings where both agents can make equal amounts of contribution to the task. Alright, that's it. You're welcome to ask any questions you may have.